Hey, hello guys, welcome to the another lecture series on electric potential and capacitor. In the previous video we discussed about a capacitor, what is a capacitor, and different types of capacitor, and we also discussed parallel plate capacitor, and we derived an expression for capacitance of a parallel plate capacitor. All right, so in today's video we will discuss about energy stored in the capacitor, and also there is something called electrical energy density. So these are the two important concepts that we are going to discuss. All right, so let's get started. The first thing is energy stored in the capacitor. Energy stored in the capacitor. Alright, so now let us consider a capacitor. Alright, so here I have considered a capacitor which is connected to an external charger whose potential difference is capital V. And this capacitor is currently being charged. Okay, it is not fully charged and it is currently being charged. So let us say the charge on the left plate is plus Q and the charge on the right plate is minus Q. And let us say the potential difference across the plate at this instant is V dash. Okay, so it is not fully charged. If it is fully charged, then the potential difference across the capacitor will become equal to potential difference across the charger. But at this state, it is being charged, so therefore potential difference across the plate, let me take it as V dash. Okay, and that's going to be less than potential difference across the charger. That's why it is going to be continuously being, it will be charged. Okay, it will be getting charged. So now let us say dq amount of charge is being removed from this plate, okay, and deposited on this plate. Okay, dq amount of charge is being removed from the left plate and deposited on the right plate. Now obviously you should have done some amount of work. Potential difference between these two plates, I have taken it as V dash. It means what? The work done to take a 1 unit charge from one plate to another plate is V dash. Now how much charge am I taking from one plate to another plate? Dq amount of charge. So therefore how much will be the work done? It is V dash into dq, isn't it? So I'm going to write, let V dash be the work, be the potential difference across the plate, therefore let V dash be the potential difference across the plate, and dq be the small charge transferred from one plate to another plate, okay. Therefore small work done dw for this process of removing a charge dq from one plate and depositing it on the another plate, the small work done will be V dash into dq, okay, V dash into dq. And now how do I find out V dash? Don't you see, the V dash is nothing but the electrical field into distance between the plate, okay. So electrical field multiplied by distance between the plate will be nothing but V dash. And actually we don't want that. What we can do is, I know that C is equals to Q by V, isn't it? Capacitance, we know that C is equals to Q by V, and in this case V dash. Why? Because the potential difference across the capacitor is what? V dash, okay, and the charge on any of the plate is V. Magnitude of charge on any of the plate is V. So C is equals to Q by V dash. So therefore V dash can be written as Q by C, isn't it? Right. Alright, so now we will substitute this V dash as Q by C. So what do we get? dW is equals to Q by C into dQ. Now this is a small work done to transfer dq amount of charge from one plate to another plate. Now I want to know total work done to transfer charge capital Q from one plate to another plate. So therefore I'm going to write total work done to transfer Q charge from one plate to another plate, is capital W. That's the total work done. So that how do I get? Integrating all the small work dones, to charge it from 0 to capital Q. Will give you the total work done. And this total work done is nothing but the energy stored. It's very simple to understand. See, whatever energy that you have spent in order to transfer the charge from one plate to another plate will be stored as a potential energy. Okay, it is just like you have a catapult. Okay, you have a catapult, and then you put a stone and then you stretch it, you pull it back like this. So when you pull, the energy that you have spent, the muscle energy that you have spent, is getting converted and is stored as a potential energy in the rubber, right? Then moment you release the stone, the potential energy stored in the rubber will get converted into kinetic energy. Moment you release the stone will fly up with high velocity, right? It will just go like that. So now what is happening here, the energy that you spent in order to stretch the rubber is getting stored as potential energy in the rubber band, and then moment you release it, the potential energy stored in the rubber band is getting converted into kinetic energy. The same principle. So whatever energy that you spent is stored as potential energy now. Okay, and when you connect that capacitor to an external battery, the potential energy will get converted into electrical energy. Okay, the energy stored will be used to send the current through the external wire. So energy is conserved here. Okay, so there is no violation of conservation of energy in any way. All right, so now I'm going to write this W as nothing but energy stored in the capacitor, which I'm going to write it as capital U. And when you integrate this, here the C is constant, so you can bring it out. Integration of q dv, limit from 0 to capital Q. Now you should remember integration of x power n dx. General formula, integration of x power n dx is x power n plus 1 divided by n plus 1. Okay, that's a general formula. Now this integration you will study in mathematics. There is a separate chapter under calculus where you will study in detail about integration. But for time being, just remember integration is a reverse process of differentiation. Okay, that means if you differentiate this, you will get back x power n. Okay, you will get back x power n. You can try this anyway. So now remember this formula, integration of x power n dx is x power n plus 1 divided by n plus 1. Now if you compare this, I'm sorry, this is actually dq. By mistake I wrote it as dv. Yeah, now if you compare these two, don't you see in place of x you have q here, and in place of n you have 1. Okay, there is nothing means what? There is 1. Okay, and in place of again x you have, in place of dx you have dq. So therefore if you compare both of them, and if you apply this formula, integration of q dq will become q power 1 plus 1, which is 2, divided by 1 plus 1, which is 2 again. Okay, x power n plus 1 divided by n plus 1. So n is 1 in this case, so 1 plus 1 divided by 1 plus 1. So here q power 1 plus 1, which is 2, divided by 1 plus 1. So limit is 0 to q. After integrating, we put this limit. This is called as lower limit, and this is called as upper limit, because that indicates what you are going to integrate. You're going to add all the small work done right from charging the capacitor from 0 to capital Q. So from where are you starting? From 0 charge till where are you charging? Capital Q. So that is what we're going to put here, lower limit and upper limit. So what do we get now? How do I substitute the limit? So take this 2 outside, no issues. You can take this 2 outside. So 1 by 2c into, in place of small q you should put capital Q first. Okay, capital Q, then square as it is. Then you should always put a negative sign, and then in place of small q you're going to substitute the lower limit. So 0 square. Okay, and this will turn out to be how much? The total energy stored in the capacitor will become q square divided by 2c. Q square divided by 2c. So that is energy stored in the capacitor. Q square minus 0 square is anyway q square, right? So q square by 2c is the energy stored in the capacitor. Now we also know that, but we know that c is equals to q by v. So therefore q can be written as c into v, right? So substitute q as c into v. What do I get? Energy stored in the capacitor as c square v square divided by 2c. So 1c and 1c will get cancelled. Okay, we get half cv square is another formula for energy stored in the capacitor. Okay, both are valid. This is also correct and this is also correct. Half cv square. This is easy to remember. Remember half mv square, kinetic energy. So it is very similar to that now. Instead of m you have c here. Okay, and here v is potential difference. There of mv square, where there v is what? Velocity. Okay, so just I'm just trying to compare and making you to remember it easily just by comparing both of them. But if you are able to remember it as half cv square, that's well and good. But you can, if you're not able to remember it, you can compare this with kinetic energy. Kinetic energy is half mv square. Instead of that m, you put c here. Then you get half cv square here. All right. Now also the same formula can also be rewritten differently. What? C is equals to v can be written as q by c here. Okay, we can that's what we get it here. Okay, so we don't want to write that. We can write C is equals to Q by V. Yes, also you can substitute C is equals to Q by V in the above formula. You will get U is equals to of, in place of C you can write Q by V into V square, and 1V will get cancelled. You are getting it as of Q into V. Okay, of Q into V. So this is another formula for the energy stored in the capacitor in terms of Q and V. So all the three formulas are valid. So depending on what data is given, you should choose which formula to use. Suppose if they are given C and V, use the second formula. Suppose if they have given Q and V, use the third formula. Okay, easy to understand. Alright, so this is about energy stored in the capacitor. And now we will discuss one more important thing called electrical energy density. Okay, so we are saying that this energy is stored now. So where is this energy stored? This energy is stored in the form of electrical field between the plates of the capacitor. Okay, we will discuss that. But before discussing that, one important note that I want to write here is, you see, energy stored in the capacitor is half C into V. Okay, what is that V? V is total, the final potential difference across the capacitor, which is same as potential difference of the charger. Now, energy stored in the capacitor is half CV, but how much is the work done by the charger? How much is the total charge that's going to flow through this charger? When the capacitor is fully charged to capital Q, then how much charge has flown through this charger? Capital Q. Okay, it was initially zero charge here, and now when the capacitor is fully charged, the total charge present on the left plate will be capital Q. So that means the total charge that has flown through this charger is capital Q. So to take 1 unit charge through a potential difference V, you have to do a work of V itself. Okay, now you are taking how much amount of charge, capital Q amount of charge is taken through the charger. So that means the charger should have done work of capital V into Q. Try to understand this. The charger has done a work of capital V into Q, whereas the energy stored in the capacitor is just half of capital V into Q. So where did the remaining half go? It got dissipated in the form of heat and the other losses. So I'm going to write here note. This is important note. The work done by the charger, is capital V into Q. This is work done by the charger. In that, only half of that, capital V into capital Q divided by 2. That's half of capital V, that's half of work done by the charger, is the energy stored in the capacitor. You see here, half QV is the energy stored in the capacitor. So then remaining half QV is dissipated. Okay, so this you should remember. Alright, so now we will move on to electrical energy density. Okay, or energy density. We will write it as electrical energy density, that is more appropriate. Electrical energy density. Electrical energy density. Now what is electrical energy density? It's easy to understand. So if you consider a capacitor, a fully charged capacitor, let us say we have a fully charged capacitor. Okay, now left plate, let us say it has plus Q amount of charge, and right plate has minus Q amount of charge. Now the electrical field between the plate will be from positive plate to the negative plate, isn't it? Yes. And how much will be the electrical field between the plate? Sigma by epsilon naught. Okay, electrical field is going to be sigma by epsilon naught. Hope you remember this. This derivation we have done in the previous video. Okay, when we discussed the capacitance of a parallel plate capacitor, we derived the expression for capacitance of a parallel plate capacitor. So there we have discussed the electrical field between these two plates will be sigma by epsilon naught. Why? Easy to understand. If you don't remember, I'll just tell it here quickly. At this point, the electrical field due to this positively charged plate will be sigma by 2 epsilon naught to the right side, and at the same point the electrical field due to the negatively charged plate is also sigma by 2 epsilon naught and to the right. So both are in the same direction, they will get added up. Sigma by 2 epsilon naught plus sigma by 2 epsilon naught will give you 2 sigma by 2 epsilon naught. 2 will get cancelled. So the electrical field between the plate is just sigma by epsilon naught. Alright, and now and at the side, at the end of the plate, the electrical field line will be like this. Okay. Alright. Okay. Now how much is the energy stored in the capacitor? I know that it is of C into V square. V is the potential difference across the plate and C is the capacitance of a plate. But what is C? C is nothing but epsilon naught A divided by D, where A is area of the plate and D is the distance between the plate. Distance between the plate is D and the area of the plate is capital A. Now if you substitute it back, you will get U is equals to half epsilon naught A divided by D into V square. Okay. And now I can also write V as what? See, C is equals to epsilon naught A divided by D, and capital V is nothing but the electrical field between the plate multiplied by the distance between the plate, isn't it? So can I write capital V as E into D, but whole square, because V square is what I have, right? So ED the whole square. And now if you simplify this, you'll get epsilon naught A into E square into B square. D square I'm going to write it as D into D whole divided by D in the denominator. Okay, and D will get cancelled. Okay, so what do I get? And 2 is missing here. Yeah, so I'll get it as half epsilon naught E square, this A into D, area of the plate into, both the plates have same area of the plate into distance between the plate will give you volume of the gap, volume of the region, the air gap between the capacitor. The volume of that region or volume of the capacitor will be capital A into D. So I'm going to write it as capital V, because volume is A into D. Okay, now you take that volume to LHS. Okay, then you will get U divided by energy divided by volume will give you energy per unit volume. That is nothing but half epsilon naught E square, and this energy per unit volume is called as electrical energy density. Okay, electrical energy density. Electrical energy density is half epsilon naught E square. So this is again very important formula for us when we are discussing a chapter called electromagnetic waves. We're going to make use of this formula very frequently. Okay, so again remember, the energy per unit volume, electrical energy per unit volume is of epsilon naught E square. So in a space, let us say you have an electrical field, and you take a small 1 unit volume. Okay, in that 1 unit volume, if you want to know how much is the electrical energy density, electrical energy in that 1 unit volume, that will be half epsilon naught E square. Okay, all right, so with this we will end today's video here. We will continue the rest of the things in the next class. Till then, stay tuned, have a happy learning. Thank you all, bye bye.